Okay, so we go to chapter 4, differentiation rules. Before that, I don't know, let me talk a little bit about the history of the derivative. So you should really have a respect for these things that I'm saying, because the reason that you are seeing here, we are able to record and everything, this is because of this topic. Okay, so let me just try to motivate you at least from two different perspectives. We want to talk about the notion of the derivative, and I want to motivate you, if possible, from two perspectives. One just from mathematical perspective, and the other one from physics perspective. Okay, so there were two scientists, contemporary scientists, one from Britain, Newton, and one from Germany, Leibniz. Okay, they were thinking about apparently two completely different problems. Okay, so let me start with the Leibniz problem, which is mathematics problem. Yes, he was thinking that if you give me a curve, so if I have a function, if you draw the function, it becomes usually a curve. So this is x, this is y. Assume that I have a curve. If I have a function, when I draw the function, for example, assume that this is the graph of that particular function that you have in mind. The problem that Leibniz was interested in, he was interested in finding the tangent, the equation, an equation for the tangent line to the graph of this function at some point on it. So he was thinking that, okay, if you give me this function, so f of x given, what do I mean by f of x given? For example, f of x is equal to x to the power of 3 plus x squared. This is a given function. So assume that a function is given to you, whatever it is, and then you draw the graph of the function, or imagine the graph of the function, and you pick a point on the graph. Yes? So let me consider this one. So let me put it here. So let me consider this x coordinate of this point to be a. So he was thinking that if you give me the function, if you give me this particular number and I go and find the corresponding point on the graph, how can I find an equation for the line that is tangent to the graph at this point? Yes? So he was asking himself, okay, if somehow we all of us have some intuitive idea of a tangent line. So he was thinking that, is there any way for me to find an equation for this green line, which is called the tangent line to the graph of this function at this particular point, and then this particular point, we call it t, and we say that this is called the point of tangency. Yes? We want to find an equation for this straight line. But if you remember your Math 1C lesson, if you want to find an equation for a straight line, you need two pieces of information usually. Okay, what are they? Can you tell me? Just to refresh your memory. What do I need to write an equation for a straight line? I need two pieces of information. Yes? The slope? Yes. So more generally, the slope, I agree. Yes? What you said is right, but more generally. You only consider the point that it cuts the y or the x-axis. But in general, you don't need to be careful about that. You just need to find one single point on it. Wherever it is, it doesn't matter. So if I give you any point on the green line, and if I give you the slope of the line, in principle, you should be able to write an equation for that straight line. Yes? How do you remember that? This is, I don't know, the people who have studied this with me, I have already given you this point. But let me just start from scratch. So, for example, let me write this example. Let me just, this is a Math 1C problem, but let us refresh our memory. So determine an equation for the straight line that passes through the point A minus 1 and 2, and its slope, I don't know, in British books they say gradient. So remember this word if you see a Cambridge book. And its slope is 5. Yes? So this is a Math 1C problem. We want to refresh our memory about that. I don't know. I solve it in 2 different ways, but I want you to learn the second method in this advanced course. Okay? So the first method is that you write the general formula kx plus m. Do you remember? You say that this is an equation of any straight line, except, is it true that I say that this is equation for all possible lines?
Not for the vertical.
Not for the vertical lines. So the vertical lines don't follow from this equation. What is the equation of a vertical line passing through 1? It is x equals to 1. And you will not be able to generate x equal to 1 by fine-tuning kn. Yes? But here, I would say that k is directly given to me 5, so I would write it here. It's 5x plus m. But m is missing. For finding this m, I need an extra piece of information which is provided for me in the problem itself. So this line is supposed to pass through that point. So it means that the coordinates of that point satisfies this equation. So this means that 2 is equal to 5 times minus 1 plus m. M is missing here. I will find it. So m becomes 7. And when everything is done, I put it back. So the answer would be y equals to 5x plus 7. Yes? That is the way that you have learned and do it. Yes? Am I right? Okay. Now, the second method, this formula is also in the formula sheet. I want you to know it and try to memorize that. I told you that make an Anki account for yourself and try to memorize things. So sometimes. So k, x minus x naught, okay? This is called point slope formula. Point slope formula for the straight line. So if you know this, what you need to do is to put the numbers in. Instead of x node and y node, you put the coordinates of any point on the line. Here in this case, x node is minus 1, y node is 2. So it becomes y minus 2. The slope is directly given, and then it becomes x minus x node minus minus 1 is plus 1. And then if you simplify, it becomes 5x plus 7 again. Yes? So I want you to, this formula is in the formula sheet. I have seen that. I will usually use that formula. So from now on, if I use that formula, please don't let me suffer. This is the formula that I need. I don't explain it. Okay? So you see that in each one of these, if I want to find an equation for the line, I need 2 pieces of information. One piece is the slope or the gradient, and one is the point on the, any point, not the point, any point on the line. So let us go back to Leibniz problem. I want to find an equation for this. So it means that I need to know those pieces of information. The point is not a big deal, yes, because I told you that f is given to you, the function is given. I told you that a is also given to you. So then it means that you can immediately read the coordinates of this point t. What are the coordinates of this point t? The x coordinate of this point is a. And what is the y coordinate? What is the y coordinate? F of a. Because I told you that f is given to you, a is given. If you want to find this height, You need to feed in this number into your function. A number comes out. That number is the height. Yes? Is that understandable for everyone or no? Are you with me or not?
Yeah.
Do you understand that exactly? So this becomes f of a. So a is given, f is given. I can calculate this myself. So a and f of a is one single point on this green line. So I do not have the problem with the first initial part, but k is missing. So the main part to answer Leibniz question is that how can I find the k value of this tangent line? So it means that the problem boils down to answering this question. What k, let me write t for tangent, what is the k value for the tangent line? Yes? And the method that Leibniz actually used to answer this question was actually completely creative at that time, and it was interesting. So he said to himself, let us assume that instead of finding, my goal is to find the slope of this green line, but for the time being, let me draw another line here, for example. Okay, this one, by going a little bit further here. Yes? So let us go a little bit further. For example, let me go h units to the right, and this length is h, and then I reach to a plus h. Okay? So I choose myself a number h, I add it to a, I go a little bit to the right, and then I draw this perpendicular line. I intersect my blue curve at this point, then I will connect these two. This line is called the tangent line. This line is called the secant line. Yes? Of course, we can calculate the slope of this orange line. Yes? How can I calculate the slope of this orange line? If you remember from Math 1C again, there is another formula for k value. If you remember, it's delta y divided by delta x. I don't remember how did you learn that. But this is y second, y final minus y initial, x final minus x initial. Yes? So that is the formula that gives you the slope of a line if I have 2 points on my line. Yes? For the orange line, I have 2 points on my line. One of them, I know this is this one. I want to test your understanding. So let me call this one. This is T. Let me call this point A. Can you read the coordinates of A for me here? The x coordinate is clear in the picture. What is the x coordinate? Everyone say it. What's x coordinate?
A.
No? For A. Yes, A plus H. What is the y coordinate? Y coordinate means from here up to here. What is that? F of A plus H. Is that understandable? So that's F of A plus H. Okay, now I want you to calculate the slope of this secant line. So let me write it here. The slope of the secant line TA is equal to the y of this, let me write it, y for the point A minus y for the point T divided by x for the point A minus x for the point T. Yes? And then let us substitute these things. Instead of y of A, I can put this in. So this becomes f of A plus h minus, instead of yt, I can put this in, minus f of A. Instead of x of A, I can put this in. It becomes A plus h. And instead of x of t, I can put A in. So it becomes A. What happens? This becomes f of A plus h minus f of A divided by h. Yes? So this one is the slope of the orange line, not the green line. Yes? Yes, so we learned that k of this secant line is f of a plus h minus f of a divided by h. This is the formula we get. But Leibniz was not happy because, of course, this is not what he wanted. He wanted to calculate or somehow find a way to find the slope of this one. But then the idea is very clever. He said to himself, why I made h so big? Let me make h a little bit smaller. And let us see what happens, yes? So let me change my color a little bit here, yes, with the red one. So instead of taking, so from here to here is h units, yes? But let me make this h a little bit smaller. So if I make this h a little bit smaller, let us see what happens. Instead of going up to here, I will go, for example, up to here. Let us consider that this is a plus h this time. Yes? And then I will do the same thing here. Yes? Okay, so this is point A. Now my point A would be this one. Yes? Instead of having that point for A, this will be my new point A. So it becomes A plus H again, if this is my A plus H. The same thing, everything, the calculations remains intact, yes? Everything, if this is new H. But the point is that if I draw this secant line, what happens now? This secant line still is not the green line, but it is clear the slope of this one is a better approximation to the slope of this one rather than the slope of this orange one. So it means that I am getting closer and closer to the green line. Ideally, so it means that this point was the point A. Now this is the point A. If I still make it smaller, what will happen? Then instead of having A here, I will have A here. And if I draw the new secant line, the new secant line is still closer to what is my target. Yes? Ideally, the ideal situation happens when H is what? 0, but unfortunately, I cannot put H equal to 0. But there is nothing preventing me to be closer and closer and closer to this point T. So this can be extremely, extremely small. There is one exception that I cannot put there, and that is exact 0 number. But before that, we can demonstrate it using algebra, but I think you can also do it yourself. You can just play around with these numbers in GeoGebra and see that. After a while, your eyes cannot really distinguish between these two. Of course, I'm not forcing to buy this argument, but I'm just trying to motivate you that. To motivate you that what? To motivate you that it becomes somehow intuitively clear, not rigorously, that if I calculate K of the secant line TA and then send A towards T, this becomes K of the tangent line if A becomes very close to T. Is that understandable? So that's intuitive. I want you to intuitively understand that. This is not a rigorous argument. So it means that the slope of this one, when A gets closer and closer to T, this number approaches to the number that I'm supposed to find. In mathematics, if you want to write this, you use the limit. You say the limit of K of the secant line when A approaches T is equal to K of the tangent line intuitively. Is that understandable? So I just want to make this plausible for you. That's it. Yes? And there is one thing that you need to know about limits. I will not have time to repeat those limits from Math 3C. But when you say the limit, be careful about that. The limit of a function, when x, the variable, approaches to some number, say 2, be careful. This means that x becomes very close to 2, but not equal to 2. Yes, be careful. This is very important. When you use this symbol in mathematics, it means that x is very, but of course this have to be precise, very close to A. But this is important. X is not equal to A. So this is implicit in this sentence. So it means that when I talk about the limit, when I say A tends to, A approaches to T, it is by this symbol, I mean A is not T. And then you know that if A is T, I am in trouble because the denominator becomes 0. So what I would say is that KT is the limit of KTA, which I have a formula for it, f of A plus h minus f of A divided by h goes to 0. This is the formula that actually Leibniz got for calculating the k value of the tangent line. Yes? Of course, there is a big if, and is that how we can calculate this limit. Yes? But be careful, this limit is sensible because h is not equal to 0. It's very, very close to 0 as we want to, but it is guaranteed that h is not equal to 0 because if h becomes to 0, this argument will collapse. So, I'm not saying that I proved the formula. I am saying that I am making the formula plausible from intuitive point of view. Is that understandable? So that's a good way to calculate k of t. Okay? So now let me immediately use the Leibniz formula to calculate something. Yes? So let me give you an example. Determine an equation for the tangent line, for the line that is tangent to the graph of the function. For example, let us make it very simple. F of x equals to x squared at the point on the graph whose x coordinate is say 4. I want you to really understand this example. This is a prototype example. Yes? It's like a pattern example. You need to know this very good. It's a very standard problem. I give you a function. I give you one point on the graph of the function, and I ask you to determine an equation for the straight line that is tangent to the graph of the function at the given point. Yes? And I usually, when I want to solve this problem, I will use the point slope formula. Okay? So, you know that if you want to start from scratch, you have that formula. Yes? So you need to put a number instead of y node. You need to put a number instead of x node. And you need to put a number instead of k. If I can find these 3 question marks using the information provided for me in the problem, then I am done. X node is immediately given to you. Yes? What is x node? By reading the problem is 4. So x node is 4. But what is y node? Y node is the y value of the point of tangency. So if I want to find y node, it is f of x node. Yes? And f of x node is 4, so it becomes f of 4. But what is f of 4? Is 4 to power 2, which is 60. So I don't have any problems here. I don't have any problems there. So the only thing that is remain is calculating k. And then I have Leibniz formula in front of me, and please respect the soul of Leibniz by memorizing that. Yes, memorize the formula. Okay, so here I would say that k is equal to the limit of f of a plus h minus, I'm repeating this to memorize it, okay? H goes to 0. But I want you to understand the ingredients here. F is the function given. Can you tell me which number is playing the role of a here? What? 4. X value, the x node, yes? So let me, don't be in hurry, let me replace a with the given 4. So it becomes f of 4 plus h minus f of 4 divided by h goes to 0. So my duty is to calculate this limit. Okay, so here this becomes the limit. Instead of f of 4 plus h, I have seen students make some mistakes here, but I told you that f is like an operator. If you provide the operator with an input, the function does something on the input and gives you something back. So the role of this function is squaring numbers. It squares whatever you put in. Now you have decided to put 4 plus h in, so what will happen? It will square your input. Yes? And then minus, the same thing here, 4 to power 2. And then divided by h goes to 0. So then I have to calculate this limit. Let me remind you, I don't know how much you remember from limits from Math 3C. If you put h, first of all, you have to put this number in. But the problem is that when I put the h is 0 here, the numerator becomes 0. The denominator also becomes 0. So it is not possible to do it right now. So you need to start simplification. So let me write here on top. So you simplify this. What happens? This becomes equal to, I raise it to power 2 by squaring pattern. So this becomes 16. The first one is squared 2 times the first one times the second one, plus the second one is squared minus 16, 4 to the power of 2, divided by h goes to 0. And then this becomes the limit. This 16 and 16 are gone. Between these two, I can factor an h. I can factor an h out. Then it becomes 8 plus h divided by h goes to 0. Okay, first of all, can I simplify this h with that h? Yes? Yeah. Yes or no? Yes. Because you can simplify factors. Yeah. Yes? Don't be in hurry. You are not able, after simplifying this, you are not able to simplify this h with that h because h is not a factor of the numerator. But now if I ask you what is this, you would say this is a product. And this is a factor. So I can simplify. But more than that, if I want to simplify, I need to know something more. What is that? Because when I am simplifying, it means that I am dividing the numerator and the denominator by h. But I will not be able to do that unless I am sure that what I am dividing by is not 0. How is it guaranteed? Because h goes to 0, and then by this convention I told you that when you use that, it means that it is not equal to 0. So I am really on the safe side. I can simplify that. And then this becomes the limit of 8 plus h goes to 0. So what happens for this? Then I put 0 back again, nothing strange happens, so the answer is 8. Yes, of course, the notion of limit is a hard notion, so you need to learn it in this way. You might say that, okay, why we couldn't put, of course you realize you couldn't put h equal to 0 in the beginning, but you don't have any problems to put h equal to 0 right now. But you need to trust me on that, it will work. But it is not straightforward to discuss about these things at high school level. That becomes 8. And now everything is ready for me. Everything is ready for me. So what I do, let me clean this question now. So what I need to do, I need to write y minus y node is 16. K, I just got it, is 8. And then it is x minus x node, which is 4. And of course, you usually simplify these things. So this becomes y 8x minus 32 plus 16 is minus 16. Yes? Yes, is that understandable? So this is a typical example. I really want you to remember that. And I want to write a very important remark here, which is the essence of this. So the important remark is that, let me write it in a summarized form. The k value of the tangent is equal to no, it's not. We are not at that stage yet. Okay, so let us keep it for the time being. This is good. Okay, so let me try to see if we have some features in GeoGebra for that one as well. Just okay. So here, let me see if I, unfortunately, let me zoom in a little bit because I need 16 at least. Yeah, somehow. So here I have my function. Y is equal to x squared function here. Yes? And then I want a point on the graph of my function. So for the time being, let me zoom in actually. So this is my function. And then where was my point? It was 4 and 16, yes? So I will take a point here, A is equal to 4 and 16. So you expect that this point is on the graph. Why you don't see it? Because it should be 16 somewhere, yes? Yeah, that's your point. So that is the point, the blue point is A and 16, yes? Now you can ask GeoGebra, go here, you see tangents, you click on tangents, and then you click on your graph and the point. So you have your tangent. Yes? So that is exactly what we found. The equation of the tangent is also written here. Minus 4x. This is in GeoGebra, probably they take this as a standard form. In the textbooks that we have, we put y on one side and the others in the... But this is exactly the same equation. Do you agree with me? Yes. So why is that? Here, I don't know why they have divided by the y, this strange way of writing, but let me calculate this. So if I move this to the right, it becomes what? Minus 8x plus y equals to minus 16. I don't know how the algorithm works, but for some reason they have divided by 2. So then it becomes minus 4x, 1 divided by 2 is 0.5y, and minus 8 divided by 2 is, minus 16 divided by 2 is minus 8. Yes? And that is exactly what we find. And by the way, if you have noticed, I never tell you find the equation. I always tell you find an equation. And that is the reason. Because this is an equation I found. This is an equation that GeoGebra finds, but they are equivalent. So they are not the same equation, so I'm not allowed to use the word the equation. I have to say an equation, yes? So, but at least you understand what we calculated. You see that this is a very nice picture. Hopefully you agree that this is a tangent line. Yes? Any questions? Okay, so now let us go back to a little bit of more work for this part. Anyway, so, and then you see the structure here and the structure here are actually exactly the same. The only difference is that letter F for functions in physics, we usually use these kinds of letters denoting something. But in mathematics, we usually use F for functions. And then we use a variable here. Because this variable here is time, the good candidate for it is to denote it with t. Except for these nuances, they are exactly the same they have the same structure. Something like this happens, one in the realm of mathematics, just in your brain, just imagination, one in physical world. If something like this happens, it means that this is a really deep concept. Yes, in the world that we are living, we are solving two apparently complete different problems, but we came up with exactly the same mathematical structure. Whenever something like this happens, mathematicians and physicists get excited. So it means that there is something deeper to it, and it's worth studying it in more detail. Yes? So what I wanted to motivate you here is actually that this limit is important. That's it. So the only thing that you got from my lecture today is that pay attention to this limit is important. Yes? And when some limit or something in mathematics turns out to be important, this is the way mathematicians think. They give it a name and then they start studying it because it is important. Yes? Of course, this is not the only reason this is important. We have the application of derivatives more or less everywhere. If that question was not asked by Leibniz or by Newton, probably the history of the universe was totally different. I don't know what will happen. But everything that you are using today is somehow related to the notion of the derivative. Especially iPhones or new technologies. So for example, so you have some later, whatever is working with electricity or some kind of batteries is based on Maxwell's equations. Yes, there are 4 fundamental formulas in electrodynamics written in a nice way by Maxwell. Yes, and then for example, one of them is this. Okay, so this is the electric field, and this is the charge density, and that's just a constant. What happens here is a little bit more complicated notion of the same concept, derivative. Yes? So there are 4 equations that are a little bit more involved. For example, the next one is for magnetic field, but then it turns out to be 0. So this thing that happens here is some kind of a little bit more complicated version of what you see here. And what is related to electricity and everything is actually being calculated using Maxwell's equations. So it means that if the derivative was not there, then you didn't have these equations. And then when you don't have these equations, by the way, the prediction of people didn't know about electromagnetic waves. Yes? Maxwell did some mathematics and for consistency added some term to this, and then he said that, okay, I don't know where this term is coming from, and then later they actually discovered electromagnetic waves. So it means that mathematics is really powerful. So it means that if you follow mathematical consistencies, might be you will be able to predict something should be there we don't know about. And electromagnetic waves, probably you know that if electromagnetic waves were not there or discovered, we didn't have radios, televisions, and nothing. So what I'm saying is that this is why I want to understand that respect the notion of derivative. Yes, it is very, very important. But you will probably study that later if you go to physics courses or engineering courses sometimes. But what I want to understand from this lesson in 2 minutes is that from 2 perspectives we realize that this limit is important. Now we give it a name. The name is the derivative of your function at that point. This is called the derivative of s at t node, and this is called the derivative of f at a. So we give it a name. And then name is not enough in mathematics. You should also invent a symbol for that. Okay? And the symbol mathematicians has used so far is just f prime of a. Yes? And then they use here S prime of t node. So this prime symbol that we use here is the one that we use for the derivative. Okay? So this limit is important. It is called the derivative of my function at that point, and this symbol is reserved for that limit. Is that right? So from next session, we want to explore some consequences of these formulas and to see what will happen. Okay? So this is actually one of the very important lessons. I really want you to learn this in a very good way, especially if you go to technical programs. Any questions? Okay, thank you.